Bismillahirrahmanirrahim. Dear friends, this is our third video in the context of steel connection design. In this video, we will learn how to model and design this connection on the software IDEA STATICA. This is the connection for the truss that we have designed in our steel design course using MIDAS GEN. Let me show you. This is the shed that we are talking about, and this is the connection that we'll be designing today using IDEA STATICA. One important thing while modeling and designing this connection, the top chord connection, I forgot to add an important operation. Let me show you first the stress diagram. This one is the stress diagram, right? We can see that the purlins, these two purlins are seated over this plate of top chord, so there must be some stresses over there. And if we can see the stresses in contact, so the software automatically create contacts between this plate and the plates of these purlins, the webs of these purlins, but technically there must be some contact between bottom chords of the purlin and the top chord of the truss, but we cannot see any contact stresses here. Why? Because we forgot to add the contact operation between these two plates. So it is very much important, otherwise the result may affect. We can note these results without contact stresses that we here the bolts are utilized as 20.4% and the welds are utilized as 80.5%. Alright, so let's go to the design tab, go to solid view, and let's add a new operation, bolt, grid or contact, and change it to contact. And there must be the contact between two plates, one for this purlin 1, purlin bottom flange 1 and top chord web 3. So these two are members, purlin bottom flange 1 and top chord web 3. Alright, so these two plates have been selected. Now we can turn on the transparent view. Now we can see that these two selected plates and the overlapping area is highlighted as red. So this is the contact area between these two plates. So we must have to add this operation to the software to tell the software that these two plates are in contact as well. But the plates which is connected by bolts or welds, the software automatically take into account the contact between these plates. Similarly, we will copy this operation and change it for the another purlin, purlin 2 top flange 1, purlin 2 top flange 1. This is the top flange because its local z-axis is upside down, so it is top and it is bottom. Alright, so it is okay. Now we can calculate the analysis. Now we can check the stresses in the connection. First, see the difference in the analysis results. Now the bolts have been utilized only 7.4%. Previously it was 20%, and welds are utilized as 33.5%. Previously it was 80%. So there is so much difference between this. Now we can see the equivalent stress under the purlin's plate. Equivalent stress fields also changes, and we can click on the stresses in contact. Now we can see the stresses in contact areas of purlin and top chord. Alright, so this is very much important in the analysis, so we have to incorporate this contact. Now let's move on to our new connection tutorial. In this connection, this is the I girder, and this one is the bottom chord of the truss, and this one is the top chord of the truss. These two chords are seating on this I girder with the help of a cleat angle. This cleat angle is welded over the top flange of this I girder and bolted into the bottom chord of the truss. So let's move on to the software screen. Before getting started, if you are new to our channel, then please hit like and subscribe button and share as well with your friends, and let's learn structural engineering together. One more thing, we have already started design course related to reinforced concrete structures. If you did not watch those videos, then please go and watch those. Links of those videos I am sharing in the description of this video. So let's get started. Let me show you the center line of this structure. This one. This is the connection that we will be designing today. Go to the connection. For this connection, we will not use any predefined templates. Rather, we will model the connection by using the blank project. So by clicking the blank project, there are no members, there are no load effects, and there are no operations initially. So we have to create each and everything by ourselves. So let's begin. First we'll add a member. So click on new member, and first we will add the I Girder, which is having the section of W200 by 15. So this one. So this is the section W200 by 15. On this, our truss are to be seated. So this is not the ended member, but rather it's a continuous one. Now we will add another member. So just copy this and go to add and select for the tube HSS. This M2 is not a continuous, but it's an ended member. Its beta direction should be 90, and since this section must be seated over the I Girder, we have to give some offsets. So just first open the local coordinate system for each member. So we have to give the Z offset first. Let's try 150. Let's just 175. So it's something okay, right? We have to give the offset in the X direction because we don't want it to be seated in half width of the flange. Just give it X offset in negative direction. Let's say -50. So it's okay. Now we will add another member. So just copy it. Pitch should be 13.5. The top chord angle. Right, so this one is okay. Remove this offset. Now since this member M3 must be welded over the member M2 such that some of its part must be cutted, so we'll use the operation cut to do so. Let's right click on operations, new operation, and use the operation cut. Now we'll cut member number 3 and cut by M2 web 3. So just select M2 web 3. So it automatically picks up the correct connection, right? And it's automatically increase the length, whatever will be the required one. So it's automatically adjusted by the software. The cutting method should be bounding box, and direction should be parallel, and there is no offset. All right. So it's okay. Now since our box section are having the thickness of 3.2, so we cannot give weld thickness more than that one according to AISC specification. So we'll give 3 mm welds, and it should be on the outer side only. Right, now we will add a cleat angle to connect this tube with this top flange of the girder. So to do so, just click on the new operation and go to the stiffening member, and we will add a cleat angle manually having the height of 150 and width of 100, thickness of 6 mm, web flange joint radius and flange bevel radius as 0, and okay. So this is our cleat angle oriented like this one. So we'll have to change its directions and give them some offsets to place it at the right position. So just give it beta direction as 90. Alright, and first make on the local coordinate system and give them the offset, Z offset of, let's say 150. So it is more, let's say 145. Some horizontal offset in the Y direction as 100. 100 is more, let's say 95, 98. 98 is okay. This is 145. 147. So 147 is okay. Now we have to set its length. its length should be equal to the flange width of the I girder. So let's check what's the flange width. It's 100. So its length is actually 2 parts. So let's L1 should be 50 and L2 should also be 50. Right, so this is okay. Similarly, we'll copy this stiffening member and give it beta direction as -90. Right, so this is okay. Now we have to connect these cleat angle and tube together with bolts. So let's just click on new operation, bolt grid, A307 half inch dia means 12 mm dia bolts. Okay, so we have to connect 4 items now. And what are the 4 items? This plate and this plate, this plate and this plate. So these are the 4 items which is to be connected by bolts. What is the first one? SM2 web 1. So all are the members first. SM2 web 1, and the second one is M2 web 4. M2 web 4. Third one is M2 web 2. M2 web 2 is also selected, and the fourth one is SM1 web 1. So all 4 are selected. So this is connected now, but we have to change the location of our bolt. Let's first give it the position of 0. So it is here. Alright, so let's give it 50. So it is outside, so -50. Alright, now we want to give 2 rows, so one row at 0 and the other one, let's say, at 50. Alright, I think 50 is less, so let's make it 60. The center to center distance of bolts is 60 mm, so it is okay. Now we have to weld this cleat with the top flange of this I girder. So we have to create new operation as weld edge to surface, because this edge, this plate's edges and this top flange surface to be welded. So what's the member? Member SM2 bottom flange 1, SM2 bottom flange 1. And what are the indexes? Let's select transparent. Index number 1, 3 and 4. So 1, 3, 4. 1 space 3 space 4. And the second plate should be M1 top flange 1. So it's also a member M1 top flange 1. So welds have been generated. One-sided weld. And what is the minimum plate thickness? It's 5. It's 6. So let's say 5. So let's just take it as 3 mm weld. Alright, so it is connected. Now we have to copy this weld for the other side cleat. So that is SM1 bottom flange. Let's just select SM1 bottom flange 1, and it is okay. All the things remain same. Right, now since this bottom chord of the truss is seated on the top flange of this I girder, so it must be in contact with this. So there is a contact between this plate of this bottom chord and the top flange plate of this I girder. So we have to give the operation called contact. So just go to bolt and grid or contact and select here contact. Item count 2, because there are only 2 plates which are in the contact. The first plate is M2 web 1 and the other one is M1 top flange 1. So by viewing the transparent view, we can see that there are 2 plates have been selected, and the overlapping area is the contacting area, which is highlighted as red here. It is necessary. Why? Because we have to tell the software that these 2 plates are in contact with each other, otherwise it will not consider it. One question arises here, why we are not providing the contact between this plate and this plate, similarly between this plate and this plate, this plate and this plate, and so on. So because let's say SM2 web 1 and this M2 web 4 is in the contact as well, but this contact must be built up by these boards. Since we are using the boards, so it automatically take care of the contact between these 2 plates, similarly between these 2 plates. And since we are using the welds here, so it is understood that these 2 plates are in contact through this. But we did not use any operation to tell this software that these two plates are in contact. Alright, so we have to create the operation named contact. Alright, now since on site it is not a good practice to make this opening as it is, we'll use a capping plate to close this opening. So right click, operations, and go to stiffening plate, transparent, and this plate must be of the same size as that of the tube size, 152 by 152. So half of 152 is 76. It should be on 90 degrees, minus 75, minus 50. It is okay. Thickness, let's just use the thickness of 3 mm because it's only used as capping, and let's Z offset as 175. It's okay. Right, now we have to give the welds for this plate because we cannot leave it as it is. Copy this weld SP1, this plate SP1, corner 3, edge 3 with M2 web 3. Let's make another copy, edge index 1, and with the surface of M1 top flange 1. Now we'll apply some load effects, so new loads. Now we'll go to our model and let's find out the load effects for this connection. So this is our model. Let's select this truss and this girder only, and in this truss let's select these members. Now go to results, forces, beam diagrams. The governing load combination is load combination number 2. Let's first find out the axial forces value. Next, let's click on the quick view to thoroughly check what are the values. Let's click on the member and let's again select the governing load combination component. Fx means axial force and its value is at the ith end is 9.98 exponential 1 means 99.8. so let's take it as 100 kilonewton as a tension force in the bottom chord, and at the top chord it is 1.037 exponential 2 means 104 kilonewton. To find the shear force direction, let's first go to the section properties, right click property. Since the section's horizontal axis is y and the vertical axis is z, fz component, it's minus 5.5 kilonewton, and fy is minus 3.5 exponential minus 0.4 means it's negligible. So let's leave it, only take it minus 5.5 in the downward direction for this member, and let's click on this. It's minus 507. It's 5.1. Let's say it's 5.1 and it's 5.5. Alright, so M2 is the bottom chord and it's having the tension force of 100 kilonewton, and M3 is for top chord and it's having a compression force of minus 104. And let's open the local coordinate system. For the bottom chord, the vertical axis is z here, right? So make sure to correctly apply the loads on the correct axis by seeing the local coordinate system. So Vz for M2 is minus 5.5 because it's in the downward direction, right? And for M3 is minus 5.1, right? And since in our MIDAS model there are no bending moment, let's click on My. So this bending moment is here, but at the joint there is no bending moment, zero bending. We have applied moment releases here, so there are no bending moment. Only there is a bending moment at the beam, but since this girder, this beam is acting as a bearing member here, so we'll not apply loadings here of these two members, since these two members does not carry any bending moment at the joint. So let's change its model type to NVYVZ. Okay, now let's check the wireframe model, load effects, and M2. Since there are bending moments here, as we have described this concept in our previous video, so we'll have to make it forces in bolts. So now at the bolt location the bending moments are 0, right? Similarly do so for this member as well. Okay, now let's calculate the analysis. So the analysis has been performed and we can see that plates are plastic stain of 0.5% only, bolts are utilized 2.6% and welds are utilized 75.4%. Let's first check the deformed shape because it's very important for any analysis. Click on equivalent stress, deformed. So this is the deformed shape. So let me show you the importance of contact that we have generated. Click on this stresses in contact and we can see that on these two locations we have created the contact. So it is now showing the stresses at this location. But if we do not use the contact operation, so it is not taking any contact between these two plates. So it is very much important. Right. Now see the equivalent stresses. So the maximum stress reached in the plates is 223 megapascals and the limiting value is 248 or 250 MPa. Since we have used A36 plates, unfolded diagram of the plates of the members. Similarly, just select M1. This one is the M1, member 1 bottom flange 1 plate. This one is the member 1 top flange plate. So we can zoom it as well to see the stresses. Similarly, this M1 web plate diagram, web plate image, right? M2 is the bottom flange, bottom chord of this trusses, and this one is the diagram. We can zoom it as well. We can reset it by this button. M3 we have seen SM1. This one is SM1 bottom flange 1, this plate, and so on. This is a stiffener plate at the end, capping plate. We can see the bolts calculation as well. Right click and print preview. So all the calculations associated with the bolted connections are here. And similarly we can check the welds as well. This is the weld diagram. Here is the weld and this is the equivalent stress in the welds. We can also check the welded calculations associated with the welds. We can also generate the report, and all the calculations associated with this connection can be added to this report. And we can also click on the bill of material detailed drawing button and refresh it to view all the detailed drawings of connections, including all the lengths and offsets of the holes, welds, and all other things related to this connection. And we can also import this report to Word file, and also we can import these drawings into CAD format. I'm not going in the details of this report part because I have discussed in our previous video. So this is up for today. In the upcoming videos we will design other remaining connections of this truss shed using IDEA STATICA. If you like our video, then please hit like and subscribe button and share with your friends. And you can comment below for your desired content or desired videos. I will try to make that content for you. So see you in the next video.